There we go. So this way, y'all can still watch this back as well. Because I try to record every tutor session, but even though this is focused on just exam 3 stuff, maybe some other things related, but not as potent as the newer topics. It'll be good just to use to review for the final because the final is literally around the corner, right? But we're not going to try to think too far ahead on that. Also, y'all, look at this. My poor, I've only had this for 1 semester and it's literally hanging on by one. Like, ugh, that's crazy. I think I'm like constantly having to sync along. Okay. So yeah, again, y'all can use the chat. Y'all can talk out loud. Let me make sure that I actually want to print it out. Let me print this one out. So I am going to reference the list, but we'll of course focus on wherever it is. The right, the worksheet that y'all have, worksheet 2. I also have the worksheet 3 questions. I haven't actually worked them out considering what I've had to do for my classes, but I did look at them. See, I can only come. I think I got like a picture of it. I've also worked out some problems in the textbook, especially with certain videos that I've recorded. I've seen like different problems that you could see on the tests. Where is that worksheet? Okay. I'm going to check the chat real quick. I've only done worksheet 2, but that was a string activity. That's fair. So tell me what of the worksheet 2 and anybody, please tell me what about worksheet 2 was the most grueling part or parts, because we are here to focus on that mostly. And then we can look at some other stuff. Oh, it was buried under all my articles. Oh, okay. Yes. You know what's funny is when I was talking with Gavin earlier, a student came in, Orgo student came in to ask questions, right? And one of the things that I noted is that y'all do have it kind of easy for the exams. As far as the layout, y'all have it mostly. Y'all do have some short answer, free response type questions on this one too, but it's mostly multiple choice. Whereas when I took Orgo, and even when Gavin took Orgo, all of our tests were short answer, no multiple choice, no sort of, oh, I can just eliminate this and that, or it gives you options. You have to be able to really recall. And I'll say, because I can't really speak much about the exam, but I'll say that you do need to know all the things, like the things that were emphasized, the things that were practiced. So maybe kind of consider what's in the homework a little bit. I understand the homework is sometimes made more difficult than like the exam, but like there may be some weird questions. But these worksheets honestly do reflect what you will probably see on the exam, like the type of questions, the way they're worded, the work that you put into them. So I know that it's a little daunting, Andrea, but this is where you don't want to pressure yourself about being able to recall everything off the top of your head. Use your notes, use your resources. That's what this time is for, leading up to it. That's what these worksheets are for. So that's fair. The entire worksheet, that's fair. Okay. So I guess maybe the shorter list is, what do you feel comfortable about from worksheet 2? What do you feel confident in? What do you like if you were given a question similar to one of the ones on there, you saw it, you know exactly then how to approach it. Are there any questions on there like that or any topics? Let me help out this other student to hear. Okay. So far, Andrea says ozonolysis. I agree. It is one of the easier reactions. If you look up, sorry, I have to send an email real quick. If you look up in Outlook, and so how does everybody else feel about ozonolysis? Not the mechanism, but just knowing the reaction. Like, are we good on that one? Or are we still not feeling it? Forget it. You can thumbs up, thumbs down it in the chat, or you can just, you know, share out loud. Or feel free to share like what other reactions. Hey Alex, we're just kind of chatting about like what we need to focus on in the worksheet. Definitely the easiest one. Yeah, I agree. Like it's crazy easy. Okay, so yeah, two folks are good with osmosis. That could be on the exam. And like I say that because, sometimes questions may change. Yeah, this is being recorded. Let me make sure all my stuff is open. Okay, we do not need to look at chapter 9. That was crazy. So we got chapter 8. I feel like we're gonna focus on chapter 8 tonight. Because wait, worksheet 2 is a lot of like 6 in chapter 7. Yep. We're actually at 6 because or number 6, let me say. We're gonna look at number 6 for sure because I feel like there's a lot of questions about that. Like someone messaged me about that. Oh, okay. It looks good to leave. Um, are they all multiple choice or will there be a few short responses? There is 5, I believe. Okay, I think. So kind of like what it is usually, there's around 5 questions of short answer responses. And you definitely want to know that table. So let me go ahead and just kind of get started with that, of course. So y'all remember that table that we went over kind of across 2 labs? It was on the board for 2 labs. And it compared 4 different reactions and mechanisms. But oh wait, this is where I want to be. All right, let's call this exam 3. I'm gonna go ahead and share my screen. What gets me is reagents and what they do. Some are obvious, but when predicting reaction, I get lost. I got you. So Harrison, which reactions from like chapter 8? Because sounds like it might be chapter 8. Or maybe your substitution elimination reactions, but whichever ones, which ones give you like the most issues when it comes to trying to predict products? where you feel like you tend to get stuck? Okay. It's crazy. Jake was just on here, right? And then he had dropped off. I thought he had to leave. Come to find out, the internet. So again, just know that we don't have great weather right now, and it's possible that the connection may try to falter. Okay. So Harris, I understand you're probably writing your answer response to what I was asking. But yeah, let me go ahead and just remind y'all. So chapter 7, right, is focused on alkyl halides. Any sort of, structure compound where the halogen is the focus substrate, the focus thing that is leaving or being, placed. And there's that table comparing the two substitution reactions and the two elimination reactions. What is, okay, I'm actually going to literally copy and paste what you just wrote. What's considered a good base, nucleophile, solvent, what the threshold for certain reactions are. Okay. It's crazy how our final rant. Oh, yeah. The rain can ruin a connection with inside. No, for real. For real. It is crazy. Oh, I didn't realize it copied like that. That's wild. Wow. Okay. So yeah, y'all tend to have like really good questions and notes. I'm gonna probably periodically copy and paste onto our whiteboard here. Okay. So we're gonna come back to that, Harrison, but that's a really good question. We'll use our slides for that. So much to memorize, for real. Terrified? I feel that. You know why? It's not to say I told you so, I promise you. This is where Orgo starts to feel like Orgo. Because if you really think about it, like the first half of this course was Jen Kim extension. It was just like, deleted scenes of Jen Kim, right? Oh, that's sweet, Andrew. So like y'all are now seeing content wise and learning wise what is Orgo about. And you have to, Harrison, we had this conversation earlier in the semester. Okay, we have to, look at this differently and approach a little bit differently than some other subjects. And even honestly, y'all, to be really real, this is where like it feels like college sometimes, because Orgo, like let's even take another course, a humanities course. You're being asked, maybe not always expected, but you're being asked to actually comprehend what you're learning and to be able to justify. Okay. Not just, oh yeah, it's red. Why is it red? Why is it red? You know? It's like if you were, it's going beyond just, I know that the sky is blue. How do you know the sky is blue? How is the sky blue? And people have so many different ways of explaining it. So, right, Jen Kim was honestly better. You miss Jen Kim now. Oh man, that's funny. It did have a lot of math, which is why I like Jen Kim as well. But it is a process. So you are learning that the journey and the process matters way more than just this is the answer. This is the result. Right. I'm so glad the homework helps. I'm so glad it explains the mechanisms too, because that's important. I think the book does okay. I'll use the book periodically, as y'all know. And you know, it'll be decent to kind of see like how they explain it. So sorry, look at the chat. Hey Sarah, were you gonna say something or you had a question? I put that in 6 hours. That's funny. All right. So yeah, so let's quickly go over that table because y'all, this is what you need to be able to literally, this is the one time I'll say like you've got to know just from memory. There's other things that you'll want to remember. You will eventually remember, but this right here, you just have to know. Oh, I can't get rid of it. Okay. So we had looked at this plenty of times. I recommend if you haven't already, just on its little sticky note. Mine is somewhere. So here's mine that I wrote a few weeks ago. Write on your sticky note, on a sticky note. Obviously, it's a little too late for exam 3, but do it for final. And just have it like somewhere nearby where you always go to it, where you always go to that thing. So like I'm always on my laptop. So I literally have my sticky note with the table on my laptop. I close it in my laptop. So anytime I look down, there it is. Or I can reference it really quickly. So remember that on the left side, it talked about the difference between SN1 and SN2. On the right side, the difference between E1 and E2. And there's certain parts that will kind of stand out more in determining which mechanism or reaction it undergoes, given starting material and all the other stuff. So we have substrate type, where for certain type of reactions, or let me say for certain type of compounds and what is the leading group, right, at that particular carbon that we're focused on, it is going to favor base type of reaction given that. Same thing with solvents, right? And later on down the line, we'll talk about the characteristic of the nucleophile and the leading group ability. We know that different substrate, and let me say, different substituents that would be classified as the leading group, they themselves can be categorized as good or not good, right? Or poor. And then we have rate law. Let's flip it actually. Let's say what type of mechanism it would be. Rate law. And then the products. Okay. So I would start with maybe just the middle column here and list out all the characteristics that you need to know for each reaction. So starting on the left, I'll color code. We have substitution. Okay. So SN1 is typically favored by your 3' substrates. These are ones where whatever that leading group is attached to a carbon, we'll typically call alpha carbon. And that carbon has 3 other R groups attached to it. So it is highly substituted, right? And thus creating steric hindrance. So it's really hard for that nucleophile or base to get to, the carbon, let's say when it gets to its intermediate form as a carbocation. And then SN2 is more so favored by 1'. 2' is kind of weird. It's in between. So you may want to depend more on the solvent and the reagent that reacts with the starting material, right? And so, but you could see 2' in either one. Now, there is a question on the worksheet. Like I said, I'd love to get to it if anybody is curious. But number 6, right? Gavin, I may have to actually look back at the not worksheet, the exam, but Gavin was talking about how he was trying to avoid questions like number 6 for the exam. But number 6 is interesting because you have a, where the substrate would be, you have a tertiary carbon, alpha carbon. There's 3 other R groups attached to it besides that chlorine. And then it's reacting with sodium iodide. Think back to our labs. This is why labs are helpful and important, because they give you the real world context in which these concepts are situated in to help you kind of remember them better because you're working with it, right? So remember, sodium iodide with acetone. That's exactly what we used in lab 11. That was in part 1. To see if indicated by precipitate, we have an SN2 reaction occurring. So the given, I'm just going to use my video here. So the given reagent with its with the solvent that is set in tells me, oh, this is probably SN2. But wait, it's reacting with a tertiary substrate. What's going on here? There's a part in the book, or you can, look this up outside the book. You can use other resources, right? I think I used another resource when someone asked me about this problem. I want to say it was Master Organic Chemistry or something like that. And it literally shows a table of the different rates in which each substrate type goes for SN2 or for some other whatever. And what is basically getting at is it's still going to undergo. So when we say, oh, SN2 is favored by 1', that doesn't mean tertiary is never going to undergo SN2. It's just more likely that when you see a primary, it's going to undergo SN2. When you see a tertiary, it's going to undergo or favor SN1, right? Because of literally the structure. And then you look at the reagent, the solvent. So for number 6, it's going to probably lean SN2, right? It's just going to go way slower. And that's exactly what we observed, or hopefully you observed. You may not have, because we spent maybe like 10, 20 minutes at a time each reaction. But that's what you would observe in the lab 11. Okay. So I say all that because it's just good to know background wise, what is the point of looking at the substrate and how does that relate to each reaction? Of course, E1, E2 is the same thing. So I'm going to change it. And I'm going to say E1 is like this hot pink. And E2 is like this light pink. Okay. So solvent, where's one sticking up? SN1 is occurs when you have typically a protic solvent, right? And we're saying then, let's pull up that slide. We're saying then that we have compounds that is able to, just give its hydrogen. So it's quite proton, you could say, effective or rich. My words, I don't think that's really the text words, but my way of kind of explaining it. All right, so these are nucleophiles, which we'll come back to a little later. Where's that slide? I have chapter 8 memorized, the slides memorized more than chapter 7. I feel like I skipped it. Solvent effects. Yeah, I feel like it was much earlier. We are going to come back to this slide, so definitely put a pin on 7.9. That is a pretty helpful table. It is a little confusing, but at the same time helpful. All right, I think it was, maybe? Yeah, so it was earlier. Section. Unless someone wanted to shout it out. Okay. Let's get close here. There we go. Okay, it was like way down. So I was wrong. It was on the other end. Okay, so 7.12 looks at SN2 solvent effects. And so, but you can see what we mean when we say protic versus aprotic. So, of course, with SN1 being protic, SN2 is aprotic. Let's kind of make that stand out. Aprotic. Ugh. And it's okay. Let's not use the red. It makes it weird. Okay. I just want to make the A part stand out. Okay. So what does this mean? Here are examples of solvents that are polar protic and polar aprotic. And so, excuse me, SN2 is going to be aprotic. So something like acetone. Again, we saw that in lab 11 with sodium iodide, right? You also have DMF, acetonitrile. So acetonitrile, we've seen a lot of times, right? So we're pretty familiar with at least two polar aprotic solvents because you've actually worked with them in lab, or maybe not acetonitrile you've worked with closely, but you've seen in some of our labs, like we've talked about them. You have worked with ethanol, methanol, and of course, water. You always work with water, right? So if you just keep like a few in mind, you do not have to memorize every single one, but just, hitch on the ones that you recall from lab or you find interesting, right? You may have heard Gavin actually talk about DMSO, DMSO. DMF is, one of those other ones. What's funny is DMF sounds like DNF, right? Or DNR, let me say. DNF sounds like did not find. DNR is did not read. And so, yeah, if you want to just like find a way to remember it too, you can do that. But I would pay attention to the structures, not necessarily to just draw them, but to know why it's protic versus aprotic. Okay. So again, the table and the structure drawings really show you like, okay, this is what it is. Yeah. So this table right here, you do not have to memorize all of them. It's one of those things where you can, but this table, the table that I'm rebuilding on the not worksheet, whiteboard, that one you want to memorize. So we're going to breeze through the rest of it in a minute. But let's see, besides having conceptual understanding, what would be the best way to prep for the exam with these specifically? Part of it is this table that I'm recreating here. This is the one you do want to remember everything. Sorry, y'all. Yes. And so just the protic versus aprotic structures. Yeah. So the biggest difference is the fact that protic solvents have a more acidic proton that would be more willing to leave or to be, donated, right? And so acetone, if you look at acetone, let's actually look at it a little bit closely. Each, what's it called? Atom. Wow, the name was escaping me for a minute. So the protic aspect, right? Keyword proton. Well, one proton is hydrogen. Let me not do plus. It doesn't matter. The point is there's one hydrogen or one proton. So this unique part of any compound, if it's highly acidic, right? Or if it's, it provides that protic characteristic of the whole compound is because of some type of, typically you can apply it to it having an attachment to an electronegative atom. So it's kind of funny because DMF almost looks like it's something like that. Or acetonitrile. Well, not really acetonitrile if you look closely. So, but let's take acetone. Because acetone is like, wait, you could totally have, depending on certain circumstances, yeah, you could, deprotonate this pretty good, but not as good as like ethanol. Why? Because that hydrogen that we're looking at here versus any of the ones on the terminal carbons, this hydrogen in red text, right, is such because it's attached to oxygen. Okay. And therefore, the dipole moment, the net dipole is greater between the oxygen, hydrogen versus carbon and hydrogen. So, of course, you don't have to worry about the figures of that to justify or to solve in this course, but that's the background that explains it, to put it very simply in a summarized fashion. So that is what's creating that sort of environment for that hydrogen, right? And that's what makes ethanol overall a protic solvent and acetone not protic. Maybe not cross out acetone, but you get the point. So that's why I said, pick a few that you want to connect with. You can remember all of them if you want, but pick the ones that you are like, I know acetone, right? Or I definitely remember the structure of acetonitrile, right? And you know that it's a protic for the reasons I mentioned versus ethanol, where ethanol is more protic. Okay, so if we go back here, E1 and E2 is the same. Protic for E1, and then a protic for E2. Okay, so the next thing is the mechanism. We all know at this point, we should all know that SN1 and E1 both have a more multi-step approach to the mechanism, whereas SN2 and E2 are concerted. It's one step. It happens all at once. So the movement of electrons happen more simultaneously. And your arrow pushing is, you could say, more localized together versus spread out across multiple steps, right? And typically you'll see one step. So the mechanism drawing for SN2 and E2 is much shorter than that of SN1 and E1. Okay, so we're just going to say multi-step, inserted, and then same thing, or you can write it out. So actually what I did sometimes, this part I actually wrote out, but like sometimes I would just, instead of maybe, what's it called, quotations, I would use stars, right? To be like, yeah, it's the same as that across the aisle, that way I don't have to rewrite it. So I'm not saying maybe do that on the test, but just do that for yourself in your notes. Okay. Let's see. What's in the chat? Okay. For SN2E2, you have to draw the transition states. If so, what determines the partial charge? I don't think you need to. It's good to know for like the energy diagram, but for mechanism, you typically don't draw the transition states unless you're prompted to. So you can just simply draw the, now this is for the exam, right? You can just simply draw the mechanism. right? So let's maybe look at example just to kind of jog everyone's memories of how that looks. I'm just going to go here and pull a problem from chapter 7. I'm noticing 3, step 3 here. I'm going to do that. Okay. So let's just pick one. 7.53 maybe? Yeah, 7.53. Don't be daunted, or don't let it daunt you, scare you of what's going on here. Always, maybe at this point, you always want to just kind of label what is what. So to remind ourselves of the mechanism for SN2, notice it tells you it's an SN2 reaction. That's nice. Sometimes they don't tell you. And let's label what is here. So our leaving group in our starting material, I usually would actually write SM for what is the starting material, obviously to the left. Our leaving group, let me not use arrows, is the bromine. It's kind of like, yeah, because we're in chapter 7. Okay. Given the reagent and solvent, right, that also tells us SN2, totally daunted. No. So given the reagent and solvent, right, the reagent is actually, you could call a salt, or you can just call ionic compound, because that's sodium and that nitro group, they are their ionic forms, right? The sodium is the cation and the nitro group is the anion. So they would just ultimately, you can say dissolve, dissociate. So you can rewrite them to see that with the nitro group taking on the negative charge. Fun part, when you are given a problem, let me say reaction, and you're not told what type of reaction it is, you have to determine if you're dealing with a nucleophile or a base. Is that the case in every situation, or just this one? Most of the time, you could see a salt just because they're really good providing good nucleophiles, let me put it like that. And that's actually in that slide. Where is it? It was this one. This is the end of the slide. Where's the slideshow? Where is in here? So we have to do control find. Here it is. So this is the one I was going to come back to anyway. So 7.4 on nucleophilicity. Philicity? Yeah. In general, anions are strong nucleophiles, and you can often see them in a salt or in a ionic compound such as sodium, whatever. Right. So yeah, if you just kind of like pay close attention to the reagent, and maybe Harrison's kind of answer your question too, you can break them down into their ionic parts and state to yourself or write notes, even for Gavin to be like, oh, okay, I see their thinking process. And you can recognize what is actually going to attack. Because someone could make the easy mistake of using sodium as the attachment piece, whereas sodium is either going to form an ionic compound with whatever is the leading group, or it could be a spectator. Probably will be a spectator if it, is able to dissolve completely. So, you know that it's not going to work, because in the split second SN2, where you have a carbocation, because you technically have one, it just, you wouldn't quote unquote see it, right? Because it's in a concerted manner that it processes, right? But in that split second, it's positive. And we know that same signs, same charges repel. So that should kind of be like, you just remind yourself of these little basic things to know, yeah, sodium's not going to be the one to attack. It's going to be nitro group, right? So I know to label the nitro group as the nucleophile or base. How do you know it would be a nucleophile? It's whether it's donating its electrons or not, if it's behaving in that sense. A base is the kind of structure that's going to want to accept a hydrogen. So as I've said many times before, nucleophiles, you could say, are defined by Lewis acid base definition. So we call this a Lewis acid, and we call the base based on, I'm spelling this man's name wrong, Bronsted-Lowry, definition. So right now we're dealing with a Lewis acid willing to give its electrons away. And so it's going to do so as bromine is trying to leave, right? So knowing what we know now, and obviously, DMF is one of our solvents. It's aprotic. We saw that in the table. So with that being said, let's use a different color. Hopefully this orange stands out pretty well. So as this nitro comes in, bromine is leaving and really gets pushed out of the way, kind of, right? And that's your mechanism, everyone. This is your SN2 mechanism, right? One of the things you want to pay attention to, this is going to be in your table as well, is the fact that pretty much every time with this type of, let's say, this particular situation where you have an SN2 mechanism where the nucleophile attacks on the backside, right? Because that is the access that it's able to reach. It is going to lead to an inversion. So notice that what was originally there on that alpha carbon was on a wedge. Now the nucleophile that attached itself is on a dash. So if you are asked to not only draw the product, the new material, but also show the stereochemistry, you got to pay attention to, okay, for this particular mechanism, what is the stereochemistry effect? What's going on here? So you see that a lot in chapter 8 as well, but this is more so just in, the concern of SN2, right? So if you go back to your table, we can go ahead and just kind of put this part in. For SN2, an inversion occurs simply because of the nature of the mechanism. You just saw it, right? It came in on the other side of bromine. So it's going to be positioned in space differently than how bromine was. With SN1, you could have a racemic mixture. So that's referring to let me use a different color. That is referring to the configuration. Right? And it doesn't mean that we're automatically talking about enantiomers. I want that to be clear. Just because we say configuration does not mean we automatically are dealing with enantiomers. It just means you have a chiral center, right? So that was one of the first things we learned before we got into what is an enantiomer. I thought nucleophile was Lewis base. Maybe I am naming it incorrectly. Let's double check. Let's look up Lewis acid definition. Okay, so yeah, it is the other way. Thank you, Sarah, because I'm like, all right. So Lewis acid is a chemical species that accepts pair of electrons. Chem talk. I know a little bit about chem talk. I always like to highlight this source, LibreText. This is just literally open source textbooks. So web pages that you're looking at, like if you ever come across a web page like this. It's just like on a topic is actually coming from a book. So yeah, Lewis acid is a compound with a strong tendency to accept the electrons. So yeah, so I need to write a base. Is also much to keep up. Taking mass when it's recording. Yes, the recording will be posted. I'm actually keeping the recordings for exam 3 in a playlist this time because we've had so many already, or it feels like it. And I also do like solo recordings. I'll just go over something, and because they're stacking up, I'm like, I don't feel like posting so many links in Canvas. Let me just put it in a playlist. So when you go to Canvas, and Sarah, I'll need to actually send this to you. When you go into Canvas, y'all, and you go to tutor recordings, you'll just see that it's a playlist and it will update. Okay. But yeah, it's a lot of details, a lot of details. And so this is where you want to just know the facts of things back here. Oh, wait, no, this is where it was. All right, so I need to fix that a nucleophile is a Lewis base, and then a base is a base in terms of Bronsted-Lowry, right? Okay, so there wasn't nothing else to say here, but going over the mechanism, hopefully that cleared some stuff up. Okay, so yeah, we're making our way through the table. Y'all, my brain, it made me think of that song. All right, next thing, rate law. Rate law is not that bad. I promise you, it's not that bad. It's just you have to kind of remember which is which again. So just a lot of other things. It is based on the situation, like what's going on. So, okay, just by, looking at my table, and you're probably following along in your notes, you learned from the board that the rate law for SN1, same for E1, is constant K times the concentration of the substrate. So it is purely based on the concentration of the substrate, right? Which is going to be probably, you can say, directly related to the ability of the leading group, right? So the more of the compounds that have a good leading group, that where that group leaves, right? The greater the rate of producing the desired compound, new compound. Okay. Whereas SN2 is dependent on two different, or, two things, two concentrations, not just the substrate, but how much of the nucleophile you have. Right. Because again, the way that the mechanism works, that nucleophile is very abrasive. It's coming in, elbow jabbing and everything. So you can recall that the way that the rate law is written for SN1, that's your first order rate law. And then SN2 is second order, right? Because there's two things. So put 2 and 2 together like that. So yeah, it's the same for E1 as it is for SN1, and then same for E2, like SN2. So I'm not going to rewrite it there. But that was actually kind of easy to remember, because you can say, oh, first order SN1, 1. Second order SN2, 2. Right? That's probably the easiest one to remember of the list. Good. So as far as unique products, you see that with the substitutions. You don't really see that with E1 and E2. You just know that you're going to get like an alkene or alkyne. Currently for this exam, we're just getting an alkene. So if you wanted to write anything beyond just what was in the table, you can just tell yourself in your notes for E1 and E2 that we're forming an additional bond wherever that carbocation was. those. Okay. So now getting into some of the last two nitty-gritty things. Leaving group ability is really good for SN1 and E1. As long as you remember this, you can by default, maybe in your head, you can say by default, this make okay for SN2 and E2. You can use the mechanism to help with remembering this because that's your justification. Why is it okay, the leaving group okay, and leaving in SN2? Because it's not really able to leave on its own, right? That nucleophile says, I don't believe in you. I'm just going to push you out the way. Like, make it personal, make it personable, right? So the way the mechanism undergoes explains why we say that the leaving group ability is okay for SN2 and E2. SN1 and E1, though, the leaving group is actually able to leave. So that's the characteristic it's explaining. I meant to make these like the colors that they are, but whatever. Okay. Last but not least, in terms of substitution, because we don't have to measure this really in elimination reactions, for nucleophilic strength, okay, it's pretty good in SN2. Again, that nucleophile got good elbows. It's pushing that living group out the way, right? But in SN1, the nucleophile doesn't have to be that strong, right? Because it's pretty much going to wait until the whatever substrate it is, it leaves. I almost dropped my drawing pad. So I would even say, as far as strategy for remembering this table, because so much there's more to write for the substitution side. If you just remember the substitution side, you'll remember the elimination side because they share a lot of the same characteristics, like the way in which we would describe them. And then elimination doesn't even care to mention, to know anything about unique products or nucleophilic strength, especially the nucleophilic strength, because that is not really relevant to the way elimination occurs. So you can leave those blank or put little dashes there for it. This table, y'all have to know. I can't make this any clearer. Can't emphasize this any more. Y'all got to know this table. And I would suggest that you write it first. You're going to hear something from Gavin, if not already. You want to write this first because we call this like mind dump. Just get it out of your mind. Put it on paper, right? Because when you write your thoughts on paper, it actually saves you time and energy for working through and recalling things. You know, there is so much, like Andrew was saying, there is so much to know. Write it down. Just get it out of your mind, put it on paper, have it in front of you. Because I guarantee you, you're going to be working and then you're going to be like, oh man, what was I? Oh, there's a note to myself about this. So you do that and it'll save you so much, so much. So you'll need to know this table and then, of course, how the mechanisms actually go. So we looked at SN2. How do we feel about SN1? I may just go to an example, but do y'all feel pretty good about how the mechanism for SN1 goes?
I think I'd like to see an example if that's okay.
Okay, cool. So let's look at an example. Oh, this is like a general. No, I don't use that. SN1. All right. So we know that both SN1 and E1 have multiple steps, considering there is an intermediate. There's going to be, a couple things that we have to shift around or whatever. So looking at SN1, let's see. here is an example already drawn out, the whole mechanism. So we know that it's going to be at least 2 steps. The first thing is the leaving group leaves. It has to get out the way. But our nucleophile is not going to immediately attack until after it is completely gone. So the thing to remember with that is it's forming an intermediate step. It's forming a middle point, right? And it's like a checkpoint. All right, do I have a plus sign here for SN1? Yes. Okay, now proceed with the nucleophile. And so we get, in this case, we have ethanol. We get our nucleophile attached. And there it is. Now, it's not necessarily done because this oxygen in this example, this oxygen would not necessarily want to carry that plus sign the entire time. So the reaction is still kind of underway. There's still going to be something that goes through that occurs in order to stabilize. And that's like the name of the game with Orgo is stabilization. So we know that probably not ethanol, but like water will come in and deprotonate this part of the compound. And therefore, oxygen is neutral. So that's like the last little step in presenting the final product. You really want to make sure that your product makes sense. You don't want to just leave it like, first of all, don't just leave it at the intermediate step, right? Because that's not your final product, right? That's not going to be what actually presents, right? Just really thinking about it. You know that the final product in these sort of reactions is going to be with SN1, a full substitution, and with elimination, typically an alkene. So make sure that when you're finished, like you're at the end of something, you know you're at the end because the product is what they asked for or what would be expected for that type of reaction, right? So again, in this example, you don't want to leave that plus sign on oxygen. What do you need to do? You need to deprotonate that. Does it show it here? Yeah. So it shows it just right underneath. So it is actually showing ethanol coming in to take it. So ethanol, just a lot of ethanol, I guess, because it can be a solvent. It comes in, takes the oxygen. The electrons that were bonding, that was showing the bond between oxygen and hydrogen, just attaches itself to oxygen. And so it's now happy because a neutral, stable oxygen in a compound has 2 bonds and 2 lone pairs. Okay, so this would be the final product. But the general mechanism is leaving group leaves, then nucleophile comes in. So you'll see, as far as drawing the mechanism, you'll see an intermediate. So let's look. Ooh, probably good to go over energy diagrams. Well, let's look at not that, but like an actual problem that we can work out. And I think I can do something like, yeah, okay. So if we have enough people in here, we can totally do like a workshop thing. And y'all can work on a problem together. Yay. But like seriously, don't do science alone. I think if we have time, if y'all, feel comfortable, we can do like right now we have 4 students. We can do 2 in a group and then y'all each get a problem and then you can share out. All right. So let's see here. All right. So let's take G, for example. In this problem set, it says to draw the carbocation. The video's out the way. Draw the carbocation intermediate that is expected when each of the following alkyl halides undergoes ionization. In each case, if the carbocation is resonance stabilized, make sure to draw the resonance structures. So that would be the case for probably F, H, E, since they actually have electrons that can be delocalized. specifically those double bonds, but I am deliberately avoiding them for now. Let's see. So instead of what they were basically prompting you to do, we're just going to say, draw the mechanism for this SN1 reaction. And let's just use ethanol again. All right, so we're going to do this one together. Highly recommend you actually do it in your notes with me. All right. So from memory, from practice, this should kind of feel like, same old, same old. But just a little practice here. I'm just going to do like straight arrow here. Yikes. I know. So here we have ethanol. Okay. And it's good to draw in your lone pairs. Sometimes you don't even have to draw all of them. Just draw the ones that you're going to show actually doing the attaching. And because we are talking about an SN1, right? This means the leaving group leaves, forming our carbocation. And then this over here. Sorry, I'm having like drag our videos around. And then we have our, let me say this. I'll say reagent. Then our reagent, nucleophile, will attack. And then the third option, if needed, deprotonate. In this case, we will. So we're going to show our leaving group leaving first. And I guess technically we don't need that yet. Well, I'll just leave it. That's fine. It's just not doing anything right now to it, stepwise. Okay. So here is our intermediate. Whether looking at our starting material or intermediate, someone to chatter out loud, anyone actually, anybody, all people. What type of, let's say, group substrate do we have here? Is it primary, secondary, or tertiary?
Secondary.
Let's see. Close. What would make it secondary? The carbon. I have two. Yeah. Right. So that's pretty much it, right? So you're just counting like every, outside of bromine, of course, every like point that represents a carbon in this case. Wait, excuse me. Yes. So because there's 3 attached to this carbon that I'm going to a little dot on, that tells us, yeah, there's 3 R groups, tertiary. Now we're going to show the nucleophile coming in. Okay. And so we are going to now have our, what you call it? I'll probably just draw like this. Okay, so we have our nucleophile attached. So you can leave ET as the, for the group name, or you can actually draw ethanol. Right? Remember ethane, ethanol, sorry, ethyl is 2 carbons. In this case, it's CH2, CH3, and that's attached to the oxygen. Okay. And then you have your hydrogen over here. So that hydrogen is going to be deprotonated. And so just like in the book, it shows ethanol coming in to take it. So it's going to take the hydrogen, and then the electrons just going to go on the oxygen. That plus sign is going away, right? Oh, I meant to ask, which out of the three, primary, secondary, tertiary, which of the three in this situation is considered more stable? In other words, that plus sign, which would it be best suited on? Yes, tertiary. So you can think of it like covering. That alpha carbon is covered better with the three R groups. And so it's like, what's the term I'm looking for? Literally the word it had escaped me. But it's just more stable in this sense. It's it's going to want to be more stable versus being susceptible to. There we go. Susceptible to any sort of attack. There you go. Right. And this is showing a more, you can say, thoughtful process towards a desired compound in and of itself. Right. Okay. So to finish this part out, because again, this is not the final product. You want it to be as stable as possible. This will be our final product. Right? What do we call this functional group? Oh, wait, let's do it like this. What would we call that functional group? We have an oxygen in between two R groups, two carbons. Let's see. Yes, either, ether, right? Either or. So we pretty much formed an ether, or, made it into an ether when it was originally an alkyl halide. Okay. So that is what an SN1 mechanism will look like. It will generally follow these same steps, but you're paying attention to, again, the nucleophile itself, the solvent, if presented. In this case, ethanol is kind of like good on its own. How the leaving group will behave, and then you're making sure you're drawing your arrows correctly. It seems simple, right? And it is. I would argue that it is. But you want to just be very specific and thoughtful, right? It's like math, but without so many numbers. Were there any questions about SN1 mechanism? Here. I wish these would show like answers for all of these. Okay. All right. So in a nutshell, I know we didn't cover too many examples here, but in a nutshell, this is chapter 7. All right. There's like so many other things, too many questions to ask, but okay, I appreciate it. All right. So I know that y'all wanted to go over the worksheet. I'll still ask, were there any specific problems y'all wanted to look at? Which questions? I did do a video on question 6 from this worksheet. While y'all are thinking up of things, I forgot that I had coffee, so I'm gonna go get my coffee real quick. So I'll be right back. All right, y'all. I had to make a new pot because all that water just boiled off. And I desperately need it. Desperately need it. Oh my gosh, I just saw you. Thank you for the cover. Mine was funny. And yes, coffee at this hour. So y'all know I'm a student as well. I have a presentation this Wednesday. I had a paper due this Thursday, I decided to get it done early and actually turned it in early this morning because I said I wanted to get it out of the way because I did not want to get caught writing it like the night before or the day of, and I have other stuff. So I said, let me just get this done early. But I want to get a lot of my presentation done tonight so that I don't have to stress about doing most of it tomorrow. And it's a pretty big project. Maybe not big, but it's the major project. So yes, I am drinking coffee at this hour. It's like my little, I don't know, but I need it. I need it. Anyways, I promise I'm not yeah. Okay. So what are we thinking as far as this worksheet? Do I even have like a digital copy? Maybe not. Like if I'm looking at this, y'all can do number one. Y'all can do number one. Do you have questions about number one? Let me know. Two, maybe a little bit out there. Excuse me. And this is why I need coffee because I'm yawning already. I can't go to sleep after this. I'm sorry. I need to be up still working. Give me an example of what coding and input solving. Or I think y'all can answer actually because we talked about it, but like that you can draw from the tables. And actually, we probably want to revisit the table on nucleophiles. So maybe we can start with 5 because 5 kind of looks at all of it together. You have the potential to see even some stereochemistry. In fact, it says clearly indicate stereochemistry where appropriate. 6 is definitely one I want to go over with y'all. Okay. So Andrew, you're just like, we can just start at number 1. Is that what you're saying? I know Alex, you had also requested. Cool. Um Alex, I know you had requested to look at the worksheet too. Did you have like a specific problem question you want to look at? Because we'll just start with 1 and work down. And actually, if 1 is one of those ones, then yeah. Right. Well, timer on for my coffee, so I know to go check it. And anybody else from worksheet, said workshop, worksheet 2, and even worksheet 3. Worksheet 3 we can look at. In fact, let me pull that up. Oh, there is. All right. If there isn't anything else for worksheet 3, we'll just or 2, we'll just jump on in on the first question and kind of work through some of them. Like I said, number 5, I think would be good to focus on number 6. I'll go over, and then everything else more or less is just so you can practice identifying the chiral center and being able to determine like the configuration, but more so like what would it look like stereochemically? What would be on the wedge? What would be on the dash? Like that's what you're still practicing here. So let's start at 1. 1 simply is asking for you to use I know it's kind of like old news maybe, but it's still relevant. When you're drawing the enantiomers, use the Kahn-Ingold prelog rules, you can even say. So you are essentially starting with, okay, for the immediate atoms attached of each group to the chiral center, right? How do they differ in terms of their atomic size? And then you can go beyond that and look at the weight of the whole group if some of the groups have the same initial atom, like a carbon and a carbon. Okay, so now the enantiomers. 3 fluorohexane. All right. So 3-fluorohexane looks like this. 1, 2, 3, 4, 5, 6. Regardless of where you start numbering, it'll look the same. So at the 3rd carbon, we have a fluorine. Pretty simple looking compound. So I'm removing the numbers there so we can just kind of focus on actually numbering, labeling, ranking. So where I'm looking for the different groups. Now, what is our chiral center? I have another follow-up question after that. But which carbon is our chiral center? All right, I see an answer in the chat. Yes, carbon 3. How do you know it's chiral? And not just directed at you, Harrison, like anyone can answer. How do you know it's chiral? This is how I drew my compound, right? It looks like 3 things are attached to that carbon, but it's actually 4. But how do you know it's chiral? What is the definition of a chiral center? Also, I apologize. I keep yawning. Wait until I get this coffee. Yes. Good job. Good job. 4 different substituents or 4 different things, 4 different groups, however you want to characterize it. Yes. So we zoom in here. What 4 things do we have? We have the fluorine. We have 2 different, they are very different, R groups. And then a little hydrogen over here. And poor hydrogen, typically, it's going to be on a dash. It's just automatically. Because we know, compared to the other atoms and whole groups, hydrogen is the smallest one, right? And so it's going to be on the dash for sure. Now, there's a couple ways we can even kind of approach trying to figure out what's on the wedge and the dash. The like traditional classic way is what I mentioned earlier. You're using the rules based on the atomic size, or even like the size of the group, the whole group from this first like seen atom off of the chiral carbon. And make sure you are labeling chiral carbon, chiral center with the star. Without it, it's just kind of like, huh? And it helps you in notation. So if you follow the traditional way, we are going to rank each group or each first atom that the chiral carbon sees. The other thing you can do, we saw in lab that we practiced, is you put two of the groups in the plane, because technically that's what's going to happen anyway. And you're left with the two other things or substituents to battle it out for the wedge and the dash. Whichever one is the bigger one is going to get the wedge, right? Now, of course, this is a compound given its chirality. This is a compound that will be able to rotate plane polarized light. So it's single bonding. It's just the fact that it's able to rotate. It's free to rotate, that you will then have another type of configuration potential, given the fact that it rotates. So even though we already know we're starting with fluorine is going to be on the wedge, right? Everyone is probably aware of that. When it rotates, that fluorine will then switch in its steric position, in its direction relative to our, you can say, position, right? So initially we're going to draw it with it coming towards us. Okay, two things popped up. First, my little timer for coffee, and then the internet thing, connection. So just heads up. Anyways, we're gonna keep it moving. So initially, fluorine is going to be pointing towards us, and then we're going to draw its enantiomer, right? Because it has the potential to have an enantiomer, and it's going to be then drawn on a dash away from us. So we're going to draw two different configurations of this compound. All right. So again, you can either do the ranking, or you can put two groups in the plane. Typically, the longer chain is going to be in the plane, and then the other two groups are actually going to be on the wedge and dash. So those are your options mostly of how you can draw the enantiomers or the stereochemistry. So let's go ahead and do the quick ranking. So fluorine in this case is going to be always, I am not ashamed to look up notes, y'all. And I don't have this in my actual notes, but I tend to just kind of look it up. Okay, so atomic size trend. But something told me to look. Okay, I didn't want to do that. So the trend, yeah, is that it actually is decreasing. Is that saying negative? I'm actually tempted to look up like the stereochemistry. So if we do go based off of the atomic size, right? Technically, carbon is a little bit bigger. So I'm actually rethinking like my answer. Unless y'all want to argue something else. Yeah, look at that. Here, carbon is drawn slightly bigger. This one is kind of not obscure. It's unclear. $72.77. So like I said, you can put two groups in the plane and make fluorine and hydrogen battle out the wedge and dash. So you could draw fluorine pointing towards you. But technically, if we go by with carbon being the larger one, technically, you could say it would be like the right group. So this 1, 2, 3, this propyl group, that would be on the wedge. So you would number this 1, 2, 3. Okay. That means hydrogen gets 4. So then so this is one option. Now, obviously, this is not in plane. Okay. I am drawing a little bit differently. This is how it would be drawn. So if you just kind of tilt your head to the side a little bit, so you can see how the propyl group has like the little wedge. It's just saying it's coming towards us. And then hydrogen, of course, gets the dash. It's enantiomer would be the flip side of that. Now that's if we use the CIP rules. Does everybody understand how I did that? Or why this is? Or is anybody confused?
What does CIP stand for again?
It is, I hope I spelled their names right. Kahn, Ingold, Freelog. So these three scientists were the ones that standardized this ruling process, to figure out how to rank. We're, of course, going to go over whichever one we want to go with. We're going to go over what is the configuration. So that's like the first option. Okay. So the other way, like I said, is to put the chain in the plane. I feel like this would probably be the answer that Gavin would go with. Okay. So when we do that, now it's more like, okay, out of the fluorine and hydrogen, which one gets the wedge given its atomic size? Fluorine. So instead of doing 1, 2, 3, 4, it's really just boiled down to which one is 1 and which one is 4, because whichever one, it's still like loosely based off of the CIP rule, but it's reduced. So you're just saying, okay, whichever one gets 1 out of the 2 is the wedge. So then in contrast, direct contrast, the 4 gets the dash. So its enantiomer would be this. Where now hydrogen is facing towards us. Okay, so typically, whichever one you started with, it's as far as proper ranking. So whether it's through, in this case or in this case, the first ones of the two listed here right? You're going to determine its configuration. The other one is just going to be the opposite. And a lot of times it does line up then with like what is the wedge. So what is number one and then whatever's number four. So I'm curious now how what sort of configuration it'd be. Okay, so I'm going to renumber it so we can see the turnabout. So they're actually a nice like order, right? So we're going to count 1, 2, 3, 4 and follow that pattern. And what do we get? Well, that's like drawing an S. It's going left, or this will be considered counterclockwise. So when it's counterclockwise, it is going to the left. That is S. So this is our S configuration. OMG. What's funny is the way I drew it. Hold on, let's see here. So this would be 2. This will be 3 technically. Oops. I guess, yeah. So you can start at 1. This one also goes as configuration. So even though the wedges are on different on different substituents, they have the same configuration, the first two. Okay. So that means when we flip it, these other two would just be labeled R. That's just like implied. But let's see if it actually is following an R configuration. Should be going then to the right. So this would now be 1. This is 2, 3, 4. And yeah, R is clockwise, so to the right. Notice the arrow goes different in different direction. Unless, let me see. If I number this, 2, 3. That's still counterclockwise. So it's probably this. Yeah, because I guess you could say it repositions, even the 2 and the 3. It's not actually flowing the way I thought it would, but you would just flip it. Okay. Whoops, I need to do that. Let's bring this down. All right, I'll be right back. I gotta go make sure my coffee didn't actually burn away again. But y'all think on this. Share in the chat what thoughts or questions you have. Or if you have a different way of explaining it. I'd love to hear what y'all like came up with. Let's see. How do we all feel? Good question. I'm so sorry, Sarah. Yeah, that's okay. That's okay. This stuff is about building on itself, and also I recognize this is why I need my coffee at night. Uh, I recognize that we are tired. It's been a lot this semester. So I get it. I totally get it. Um, and I would not try to like beat all of this into your head. Like, you know what I'm saying? Um, practice what you can. And actually, totally meant to, excuse me. Let me get this first sip of coffee and maybe this will kind of draw me back to life. So I meant to have pulled up as well that list here, but I'm just gonna have to look for it real quick. See, three. Of course, y'all have it on YouTube. I think he shared in Canvas or in an email. Here we are. So yeah, y'all are like a few hours, several hours away from the exam. And I say that not to make you think hard about that, but just to be like, okay, from this list, I would focus on, or well, go through it first and do like a ranking system. You may have heard red light, yellow light, green light. I mentioned it before in some tutoring. And you're basically seeing what do you know? That's green. What do you kind of know? Which is yellow. What do you absolutely don't get still at this point? Where you look at it and you're like, what is that? That's red. At this point, you got a couple options. But at this point, I would probably focus on the yellow to be real with y'all because the yellow area is what you do somewhat get that you can go like maybe 80 to 100% all the way. Right. And then the red, you want to just like dabble a little bit into, but don't try to really like teach yourself. I mean, you could definitely watch some videos. I think that's probably the most lucrative, effective way to get through some of the material now at this point. But keep it simple, keep it short. Don't try to rewatch any of the lectures. Rather go through the slides and the text might be helpful. You know, it's like general enough, but I would look for I've shared the website with some really good sources, but look for sources that explain things in a succinct way. Well, there will not be any osmosis questions. No, you're fine. Um, like I can't really say for two reasons. One, I signed the academic integrity page, but then also I literally don't remember until I look at it again. That's my answer. My other answer is know all 10 reactions from chapter 8. Yeah, like we're gonna get into that in a moment. So sorry, Andrea. That's how I have to respond right now. We could totally talk about the exam afterwards. I did hear two different things. Someone told me there would not be any. Well, the question could be, are you only being asked to provide products or are you being asked to do the mechanism of ozonolysis? And that goes for all the other reactions. Now, I can tell you, you need to know the mechanism and reaction for substitution, elimination. You need to know both of those things. And they both run together anyway. So you might be more so asked to present the mechanism for lesson 2, right? Or E1. So you got to know those things because it's heavily dependent on understanding the mechanism. We know the praise we can get that for real. I mean, I feel like, but like I said in the beginning, this is feeling like actually Orgo, and you're seeing why I don't care how minuscule a topic or concept may be. You better have 2 + 2 down so that you understand the other stuff that builds on top of it, right? Like at this point, you're seeing why that stuff matters. So, but going back to what you were asking, Andrea. So you do need to know the mechanisms from chapter 7. And then this is what I would suggest for chapter 8. With chapter 8, let's not look at number 1 right now. So for chapter 8, there's, not to scare y'all, but there's that summary of reactions. Now, I'm not suggesting you memorize it from this form. In fact, this makes me anxious. I never liked seeing this summary like this. This is diabolical. I'm being so real. I prefer typically like a list, like what I literally did going through this to prepare for these sessions is I would actually go through several pages in my notebook, each reaction, listing the facts, maybe working out the mechanism. I don't do this. That's just not me. Now, someone may like this, but my point is you do have to know the reactions, the mechanisms. Most of them, some of them you will need to know, right? But they're more or less to help you with understanding how we get how the reaction undergoes. So how we get the product. So use the mechanism as a tool, but the reaction itself is what you need to know for the exam.
Can I ask you one question?
Yeah, ask me all the questions.
Do we need to know like examples of like, say it gives us like gibberish, like like the exact chemicals and will it say like what mechanism is this?
Okay. So it's a possibility you could be told what is the reaction. And then there's a number of different types of questions. Because at this point with chapter 8, you have like synthesis starting out. So you can be asked, given starting material, which for chapter 8, they're all going to be an alkene of some kind, and the reagent it reacts with, what's the product? That's the first type of question that you will probably see. The other one is the flip side. You have the product, and then you could have the reagent, and they're asking you what is the starting material. A great example, I think this might be something you can see on the exam. This is a very common ozonolysis question. So it may be asked, given, okay, 2 ways it could be asked. So given the product, what is the starting material and reagent it reacts with, or end reagent? Let's just leave it there. So what are the 2 things that come together to give us the product? All right. It may not even say what type of reaction, but you will know literally based on how the product looks. If you have a product like this, Sometimes the plus sign's there, sometimes it's not. Do this. If you have a product like this is ozonolysis. And the way I know is because that is the result of an alkene being cleaved and then turned into either an aldehyde or a ketone. You're going to see that carbonyl group on either side, right? So y'all have seen something like this in lecture. So you would put O3 and then like zinc with water. The other one is disulfide. Oh, I had that right the first time. It looks like this because I think I'm stuttering on. I think we shorthanded to DMS. It's dimethyl sulfide. So anyways, yeah. So this will be your reagent, and then your literally count your carbons. So 1, 2, 3, 4, 5. This was originally a 5-carbon chain with a double bond. 1, 2, 3, 4, 5. Boom. Okay. This is an example where you're given the starting material. Sometimes you're only asked to provide the starting material. Sorry, I think I meant to say product. You're given the product and you're asked for the starting material. So if they give you the product and the reagent, there's really only one thing to look for. If you're only given the product and you're asked to find the starting material and the reagent, you have to really look closely at what product is there, or what's the unique thing about it, and then consider what ways in which it was produced, right? Given whatever starting material, which in this case, because we're looking at chapter 8, it's going to be a bunch of alkenes. It's going to be an alkene somewhere. So these are the type of questions you can get involving a reaction. But notice I didn't even reference the mechanism. I'm not saying it's atrocious, but it's a lot. It can be a lot. So this is what you could deal with. And like I say, you don't have to remember it this way. You can if you want. I tried, did not help. I'm not talking about now, I'm talking about when I took Orgo. I was like, oh gosh, no. So whatever works best for you, right? I feel like I kind of went on a tangent, getting into oh no. Not your question though, Andrea. It was like something else I had said. All right. So did y'all want to still look at just stereochemistry and worksheet 2? Or did y'all want to practice like 5 or 6? I also have this worksheet pulled up. Seth, I don't know if you were here when I said this, but I did not get a chance to actually go through, like work it out. But I looked through it, and I guess you could say like mentally, I was like, oh, this could be, and this is of course like a lot of chapter 8 stuff.
Yeah, it looked pretty useful. I haven't worked it out yet, and I saw you said it wasn't due tomorrow. So, or at least Rose said it wasn't due tomorrow, which very grateful for. I haven't printed it out, so.
Yeah, that's cool. No, that's good. That's good. So, I mean, but definitely, pick at it, just kind of use it to help you study for the exam tomorrow. Cause honestly, that exam felt like it crept up on us. So I did pull up the topic list, and as I was saying, go through it at some point, maybe even right now, while we're here. Just kind of go through and see what are my greens, what are my yellows, what are my reds. Or if you want to do number ranking, maybe 3 you get it, and 1 you don't get it, and 2's in the middle. What's funny though? So looking at the topic list, we've already covered stuff about substitution, elimination. Just now, I technically went over 1 addition reaction in this entire session. Locate transition state and intermediate on an energy diagram. So we can obviously cover that if y'all need to. But identifying electrophile, nucleophile, the last couple of problems that we did here, I really only identified out loud the nucleophile. And so I didn't actually say the electrophile, like what is the electrophile, but that was quote unquote implied. So I'm going through and I'm seeing like what we've done in this session. Determine most stable cation. We talked about that. Know your arrows, know how to do mechanism, obviously. Naming, know rate loss. So we covered that. Predict product. So so far, half of I can even tell you from experience, majority of this exam, y'all, is chapters 7 and 8. Chapter 6, you will see some pointed questions that draw from chapter 6 concepts or topics, but it's mostly 7 and 8 because by that point, you're using the culmination of previous topics and you're actually applying them. If I were to say which one predominates, to me, it feels like chapter 7, but I think it's equal 7 and 8 because after SN1, SN2 stuff, then there's the bullet point, know the difference in meanings of Markovnikov and anti-Markovnikov, determine the major or minor products of a reaction, and that could be any of the 10. Know all 10 reactions, I agree. And then create a mechanism for reagents to form a product. I want to actually see real quick again what the worksheet 3 looks like, because this is how I would look at this list. So based on the bullet point saying know the difference in meanings of Markovnikov versus anti-Markovnikov, that tells me I need to know those mechanisms, if nothing else. Partially because, see, here's those analysis. But it's partially because a few of these reactions follow Markovnikov. Does anybody remember what's Markovnikov addition? Or let me say mechanism.
It goes to the most substituted carbon, right?
Okay, what goes to the more substituted carbon?
The nucleophile, right?
Okay, so give me an example of because some of these things you're adding 2 things.
Like an OH or something?
Okay. Let's kind of go to the original. Think back to it talking about the experiment or the observation that he had. So what was Markovnikov's observation?
I don't remember.
That's okay. So remember, initially, he observed where hydrogen goes. So like when you were talking about OH, yeah, compared to what other what other thing is attaching where you would see the pattern as Markovnikov. Remember, with him, it was hydrogen that was kind of the focal point. Yeah. So hydrogens tend to bond near other hydrogens. That's Makovnikov's observation. So if it goes that way, we call it Makovnikov, right? Mechanism or addition. And so that was first discussed. I think I'm close here. That was first discussed in not hydrogenation. Goodness, there's so many slides. Oh man. Yeah, I'm like nowhere near close. Here we go. Okay. So hydrohalogenation is the addition of a hydrogen and a halogen. And so here is where it talks about it in the slides, rather. Now, obviously, it's going to look a little different elsewhere. But in the slides, it's simply in 1869, this guy named Makovnikov observed the H or the hydrogen atoms going towards the carbon that bear more hydrogens. So that is considered Makovnikov in terms of the mechanism. So anti-Makovnikov means hydrogen is going to go towards the carbon with the least number of hydrogens, which you can rewrite as more substituted, right? And then in Makovnikov, hydrogen atoms going towards more hydrogen atom side means that it's going to the carbon with the least substituted side for carbon. So Seth, you were kind of saying like halogen or even OH, when it follows Makovnikov addition, that particular substituent is going to go towards the more substituted carbon following the hydrogen's placement. So yeah. So that list, on that list, Gavin's literally telling you, you better know this mechanism, right? So here is the mechanism in a nutshell. All right, just a little reminder. Hydrogen is the one being attached first, so it's picked up by the electrons in that double bond. Just two of them. It's not like both of them are reaching out. And then that forms a carbocation for a moment. And then the bromine comes in as a nucleophile to attach to that carbocation to stabilize, to form the product, and it's done. Okay. So when you see where hydrogen goes in a reaction such as this, if it goes to the least substituted side, you know you're looking at a Makovnikov reaction or a mechanism. So there is this one, hydrohalogenation. There's also the acid catalyzed, here it is, acid catalyzed hydration that also, I think this is what you were thinking of, Seth, that also follows Makovnikov. And what's weird is that it doesn't say it until it talks about oxymercuration. Because oxymercuration, right, which also follows Makovnikov, oxymercuration is an alternative reaction mechanism to what is called acid catalyzed hydration. So that way there are no rearrangements, like guaranteed. But you need this mercuric acetic reagent coupled with water and then NaBH4, right, to undergo the like two-step process. So there's right now we see three different reactions: hydrohalogenation, acid catalyzed hydration, here, and oxymercuration, demercuration. All three of those follow Makovnikov addition mechanism. You got to know the mechanism, right? And then, of course, relative to that, you got to know anti-Makovnikov, which again, hydrogen is going to decide the carbon with the lower number of hydrogens and therefore the more substituted side. You'll have to know major minor products. That's going to typically either be based on, the effect of stereochemistry or the effect of regioselectivity? All right. So did y'all want to, hold on, we can maybe go for like another 15 or so minutes. Did y'all want to stick to worksheet 2, which is just like chapter 7? Or did y'all want to kind of shift gears and talk chapter 8? Because we can even use this worksheet to help like practice. So share how you're feeling right now.
I wouldn't mind switching gears to chapter 8, but that's just me.
Mhm. Okay, so we got one for chapter 8. Anybody else feeling chapter 8 right now? What's your feelings on chapter 8? Are we like excited or are we just like, this chapter 8 is wild. Chapter 8, not gonna lie, is wild. And of course, you can, you know, request something from the list for the exam. Because we've talked about a lot of things, reviewed and practiced a lot of things, but there's a few other things. If you're still wanting to get clarification on, we can. So, Harrison, how are you feeling? Did you have any other questions about chapter 7, or did you want to look at some chapter 8 stuff? Maybe we can go over the Kolmogorov mechanism. Mm-hmm. Hey, it's a struggle. I got you. All right, Sarah, how you feeling? Right, products. Use vocabulary. Sorry, so you put in the chat. Okay, moving on to chapter 8. Sounds good. Okay, so what I want to just because I just thought about this. What I want to remind y'all on is there is these playlists. So they sound similar, but they're actually different. One is the set of tutoring recordings for exam 3, like this one, that I've just been keeping all in one. And then the other one are solo recordings where I'm focused on one or multiple exercises in a video. So this is what it looks like so far, 5 videos here. This one, though, I wanted to mention because I anticipated with chapter 8, we're going to probably need a lot of practice. So, goodness, it's an hour long. Sorry. There's a lot of like this, discussing things, but I did go over like a bunch of problems. Okay. So if you're still after this tutor session want to be like, I want to go over some more practice and you don't want to go into the homework, but you want to see something similar to what was to the homework or even to the worksheets, I try to pick out questions that would be close to what was on the exam or what could be on the exam and go through that with you in the video. I don't remember how many questions to a T, but this would be good to go over as well because I try to hit all or as many reactions as possible. Right. So check that out. whenever you can, or just as like a little reference thing. And I highly recommend if you do want to watch it, just put it on like the highest speed you can handle. Okay. Because I'm talking a lot. All right. We could probably start with this one. Let's see what else. 2 is cool. You know what? I like 2, but we're gonna talk it out. Okay. And since there's less than 4 students in here, we're not gonna do breakout rooms. Y'all can just kind of, unless y'all want to work on it together and I'll just mute myself. That's fine. I was just gonna like give y'all each a reaction to try on your own. So number 2, it wants you to just look at the reaction and talk about what's going on. What's funny is, so we have a strong acid here. It doesn't say that it's a synthesis. It does say to draw the mechanism. So, but what is going on? Like I said, I have not worked these out. So provide an explanation for the following observations. Your explanation must include mechanistic considerations. So it's saying your explanation must include the mechanism. I may need to really think on this one. So let's not stress about working it out completely. I just want y'all to talk it out to each other out loud, or you can use the chat again. Focusing on the first reaction, what's different between the material on the left and the product on the right?
Okay, so I know with H2SO4, it wants to put that OH group on the most substituted carbon, but I'm not sure why it made a double bond on that ring.
Yeah, so I'm considering. So what would we call the group, or what group? Well, what would we call like the whole compound given that unique OH group? How could we categorize that compound? Because it's not, the starting material is not an alkene. Over here, it's an alkene. And this is our product side. Here's our reactant side. So we see we get an alkene. What did we start with? Don't worry about trying to name the whole structure. I mean, do practice that, but let's just keep it general. What would we call this compound given the OH group?
It would be no, it wouldn't. It would be an alcohol. I know it would
It would
be
be
an
an
alcohol.
alcohol. Yeah, it would be an alcohol.
And it seems to have added a carbon into the ring as well.
Okay, so that's another major observation. That ring went from being a 4-carbon ring to a 5-carbon ring. Not to mention, there's now an alkene. Okay, what else do you notice? Do we still have an OH on our product side?
No.
Nope. Right? Clearly, no OH. It's gone. Right? This arrow indicates a change, movement of something. Literally, the OH moved out the way. taken up somewhere or it left, whatever sort of mechanism. One of the things I thought of, because this is one of the ones that we actually got to observe, this could be acid catalyzed dehydration. I also speculate there was some sort of rearrangement, although it's kind of a weird one because it seems to indicate like the ring opening up, which, could happen. And then it shifts. So it's like this part unzips and forms this. OH is gone. You see how the pieces have rearranged? Like you're just repiecing it, right? And what do we end up with? We end up with pretty much the same number of carbons, not the same number of hydrogens, of course, or maybe we do. We might still have the same number of hydrogens, but that OH group is gone. The oxygen is gone. We have 1, 2, 3, 4, 5, 6 carbons. Here's 5, 6. So the number of carbons is 6 for both the reactant and the product. If we count real quick for hydrogens, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 plus the 1 on OH. Over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. So did I count that correctly? Yes. So this makes sense for probably one reason only. The word dehydration. When you're dehydrated, like you personally, when you are dehydrated, y'all, what does that mean? What are you lacking in?
Water.
Yes. You are lacking in water. To dehydrate means to remove water. What is water made up of?
2 hydrogens and an oxygen.
Right? Or in Orgo's way of putting it, a hydrogen and OH group. Right? So it makes sense that this is probably a dehydration. It's acid catalyzed, considering the only reagent here that we see given is an acid, very strong one. Where did we see this before? We saw this in Lab 9. It was literally titled Acid Catalyzed Dehydration of an Alcohol, right? We started with an alcohol. We ended up with an alkene. We drew the reactions and the mechanisms. We even talked about which product would be major. We only see one product here. I'm assuming that's the major one, obviously. But like, this is the one product. And so I'm going to roll with that. So we lost an OH group. We also lost a hydrogen, right? And so the one hydrogen on the OH is gone, but like we also went from 11 hydrogens on carbons to 10. So together, the hydrogen and the OH group makes water that was removed. Hence the term dehydration. We dehydrated this alcohol. And the result is an alkene. That's just us talking about the reaction. We haven't even done the mechanism. I may not even do it tonight. But if you look back at Lab 9 in your manual or in your notes in the notebook, like your lab notebook, then you will be able to produce that same mechanism because we've done it before. It's a where the OH group is, it's on a 2' carbon. So honestly, you can go either way. But this may be where we see that rearrangement. This is a very unique product. You won't see this on the exam. Not this. In fact, this is chapter 12.
Thank God. Thank
Yeah.
God.
Yeah.
Thank
So
God.
you're not gonna see this on this exam 3. Right. But you have technically seen it in lab. It was just a different compound. All right. I'm gonna actually skip that reaction. All right, let's take a look at this one. Number 1. All you're asked to do is provide the reagent or the products. You're given the reagent and the starting material. So what I'm going to do, this is where I definitely want y'all to kind of like try your own maybe, unless, let's see, was there another problem here that y'all can try your own? Maybe this one y'all can try now. Hold on. Let's see how y'all feel here. So we'll do one together. If y'all feel good about after that, I'll just like maybe hint at stuff, but y'all will each have your own reaction and then you will present what you got. Okay. No pressure, by the way, no pressure. If you get it wrong, that's okay. In fact, get it wrong now so you can get it right on the exam. Right. But it's okay to make the mistake. So let's do together. Which one do you, I'll let y'all choose. Which reaction from this circle here y'all want me to go over? I may or may not actually draw the mechanism. I may just use an example. Hint, hint, hydroboration. Not, you don't need to do that. You actually do not need to worry about that mechanism.
Can you do H2SO4 H2O, maybe?
Oh, okay, I see. Yes. That one is probably, that one's going to be, should be your acid catalyzed hydration. So that's actually perfect. If that's the case, that's your Markov addition mechanism. Okay. All right. So we have a winner. Here is our starting material. Just for the heck of it, I'll name it. Let's go back to here. Okay. I'll actually double check that that is actually, unless someone wants to confirm in the chat. This is probably, sorry, now my brain is like slowing down a little bit. This is probably acid catalyzed hydration, like I was saying earlier. Okay, so we're gonna provide.
Yeah, that's what I thought it was.
Yeah, it looks like it, right? Because you have the acid, you have that would be your catalyst, and then you just have water. So all you would be adding is an OH and a hydrogen. Yeah. So okay. So keep in mind too, these are just predicted products. So a lot of it is more theoretical until you actually experiment, you see what you get. because you never know. So, what do we have for our starting material? We have here a methyl cyclohexene. Okay. There's a few ways you could name this. You can be very meticulous and actually say exactly where everything is. There's only two unique things beyond just the hydrocarbons and them being like single bond. You have the alkene and then you have the methyl group. It's a six carbon ring, hence the hex like prefix. We have the ene part to tell you that there's an alkene there. I made it a little bit more shorthand and I did know where the methyl group is. It would just automatically fall on carbon 1. And I'm just going to make this arbitrarily carbon 1. Maybe not arbitrarily. I want that substituent to have the lowest carbon number, right? So it's kind of just like, yep, there it is. Okay, so 1-methyl cyclohexene. So it's reacting with acid and water. Again, strong acid here. And given these two, we're thinking this is a hydration that uses an acid catalyst. So the full name would be acid catalyzed hydration. So that's the case. The facts follow as such. We have here would be Makhovnikov addition. Here we are. We want for it to be a hydration, we want the concentration of the acid to be diluted, therefore more water than acid. Versus, again, think back to lab. When we did our lab 9, even though the reaction you don't really get too much in this in Orgo 1 this time. We didn't add any water, actually. Water was produced a little bit, but the concentration of acid to water, right, is greater because you wanted to proceed in producing an alkene. So there's this slide somewhere that talks about that. Here it is. So thermodynamically, right, you're using the concentrations to help you go towards a certain product. So it's going to go a certain way, and you can say control like the direction of the reaction because it is ultimately at equilibrium. So if you have more water, right, because you want to hydrate, you need more water, right? You're going to have more water than acid. Therefore, you'll have a diluted amount of acid versus what we had for lab 9. We had more acid. So there you say it's a concentration or concentrated amount of acid and less water. Because at that point, the goal is to get an alkene. You don't want the hydrated compound. So this forward reaction at the top, that is what we have here. I feel way more confident now after looking at that. So yeah, definitely it's going to be acid catalyzed hydration. So let's take a look at the mechanism. So mechanistically, right, following Makhovnikov, I'm going to go ahead and write that in. So it's Makhovnikov addition. So that means H goes to least substituted side with the carbon that has goes to carbon with most hydrogens. That's the true to the observation, true definition. But we'll sometimes say hydrogen goes to least substituted side. All right. Because my brain is a little mushy, I need to look at mechanism again. Okay, so proton transfer. nucleophilic acid attack. I almost said acid, and then proton transfer again because we need to deprotonate that oxygen. Okay, so I'll move this up here. So with this setup, well, let me show for anybody that's curious. If you're like, well, I don't want to draw the mechanism. Okay, so this will be our product without really going through the mechanism and drawing it out. That's it. Again, why does it end up this way? Where's the hydrogen? Actually, did I do it right?
No, I think it would go on carbon one, wouldn't it?
And what is that thing that you're saying goes on carbon one?
The OH,
Yeah,
because it's the most substituted carbon.
good catch. Good catch. Yes. I like when I make mistakes because then y'all get to see, like, wait, not even right. Yeah. So I was wrong, right? Because I did it so fast. This is why I like to use mechanisms too. But yeah, that is correct. OH needs to be on the more substituted side. Hydrogen then is on the least substituted side because it went to the carbon with the most hydrogens. So mechanistically, right? What happens? Let me move this two and one out the way. What happens is this. So I'm going to draw. I'm just going to redraw it out like this. Technically, sometimes I like to redraw it so you can see everything. All right. So when the bonds and double bond reaches out for the hydrogen, because that hydrogen is definitely more positively charged than like any of the carbons. So the electrons between the double bonded carbons, the sp2 carbons, is attracted to the hydrogen. And then with the net dipole going in favor of the sulfur in the H2SO4, the electrons there is going to move towards the sulfur. And that's where we get the bond breaking and the movement of the parts of the compound. Okay, so we have this. Get this situated. So there is already hydrogen there, but we added another hydrogen. This creates a carbocation at the carbon with the methyl group. Now, the question here you want to consider, is that plus charge happy where it is? Or let me say the carbon with the plus charge, but is it stable? Is this the most stable carbocation we can have?
I think so, because it's the tertiary, yeah.
Yeah, exactly. Tertiary is most stable carbocation. Let me just say C plus. Exactly. So that plus sign there is good. That carbon there is fine. And therefore, we wouldn't have to worry about we shouldn't have to worry about any sort of rearrangements, one that it would want to undergo in order to stabilize itself. So now with that being said, that water can come in. Right? Because it's attracted to that carbocation. Okay. So we get the initial state of forming that OH group on the whatchamacallit, the carbon that was just then positively charged. So you could say like the plus charge moved from the carbon to the oxygen because the formal charge on oxygen now with it attached to that carbon is +1. This carbon that had the plus charge is fine. It's good. So we need to get rid of one of the hydrogens. So one of the that OH or that water group is going to be deprotonated. Okay. So in the slides here, it's showing another water molecule coming in to deprotonate it. So I'm just going to follow suit. All right. So water comes in, takes a hydrogen. So the electrons between the O and the H that is of the group we're trying to fix up here to be oxygen or OH, right, is going to move to the oxygen. And I'm just going to draw an arrow there. Okay, so draw arrow. There is the reaction, and then underneath is flow of electrons to represent the mechanism to get our product, right? So if I didn't jump to just what is the product and I did the mechanism unfolding will reveal what type of product we get. Because for me personally, the mechanism here, it allows me to pay attention closely to like the definition of Makotnikov. So I'm being very meticulous about where I am placing things, right? And the moment I like forgot and I put the OH on the other carbon of the original double bond, you know? So yeah, sometimes like once you get the mechanism down, it will help. It'll definitely help. Okay. So I'm gonna pause here. But how do y'all feel about trying one of the other reactions on your own and then sharing what you got?
Feel pretty good about it.
Okay. So Sarah, Harrison, how y'all feel about that? Y'all wanna try it out?
Can't make any promises, but yes.
That's cool. Hey, I love it. I love like the bravery. I love it. And Harrison's like, possibly. Let's do it. Okay. So y'all have, of course, like free reign on how you want to approach it. You do not have to do mechanisms. I'm not even asking you to do mechanisms. Like it helps, but that's just me. So if you're like, oh, fine, I'll need it, then go for just presenting your product. But still pay attention to the facts. You do need to know the facts of the reaction. So let's see here. So I did the one that was in the very middle bottom. Let's cross out. All right. So we have that product there. That's done. So I think ones that we can kind of focus on. Ooh, which one? Ooh. Kind of want to maybe this one together. It's question mark. I'm literally gonna do any, meeny, miny, mo. I am so sorry, but this is a good one to practice. This is a good one to practice. Okay. So these are the three that y'all will try. I'm gonna just I just want to like have this one because this one's interesting. I'm just gonna have this one for anyone to grab here. Who wants to attempt like drawing the product for this hydroboration?
I can try tackling it.
All right, Seth. Okay. So that's cool. That's cool. All right. So unless Sarah Harrison, y'all had like a preference for the other two, you know, I was just gonna assign
Or don't
which one you want to do.
I don't have a preference.
You have a preference? Okay. Harrison, did you have a preference? Because you can also think about like, oh, this would be the one I want to practice. Nope. Okay. All right. So let's see. Harrison, I'd like to see how you do with the um hydrogenation. So Sarah, you get the one at the top. Okay. Your hydrohalogenation. All right. So take a moment. I will also mute myself. You're also more than welcome to ask questions, and you can talk amongst yourselves, of course. And then let me know what you get. Everyone's going to have something a little. Hey, Sarah, did you still need more time? Or are you ready to?
Yeah, I still need more time, but I also can't access. I don't think I can access
Oh, it's okay.
captions right now.
Um, yeah, no, I was like, I noticed like the little names popping up, and I was like, what's that? And then I noticed Seth Harrison, y'all were like drawing on the screen. That was cool. You don't have to draw on the screen. So you can just like share out. I'll draw it for you, you know. Yeah, this may have to be like, I mean, we can look at something else, like that maybe the last thing, but I'm actually tired. I hate when coffee makes me tired.
That's the realest thing ever. That's so real.
That also can be a symptom of ADHD, just so you know.
I've heard that before, and I'm like, dang, do I have ADHD? Or am I just like, oh, I also think I may have dyscalculia, but who knows?
Same.
So, but yeah, y'all take your time. I see what y'all have. That hydroboration one. I had to look back at my notes just to be super duper sure because I was working it out too.
Oh yeah, yeah. I needed my notes for it.
Yeah, that's crazy. Like I actually, man, maybe I need to go through the mechanism.
It low key frightens me that I'm gonna have to do this test with no notes.
Oh yeah, no, I'm sorry. I meant to ask Gavin, um, because there is no test corrections for this one. Is he curving this test?
He's curving it
Or
and he's doing like he's gonna tell us tomorrow, but I went to his office hours today and he told me that we're doing a Jeopardy thing
Mhm.
on Thursday for extra credit. So
Yes,
I
yes.
know I'm gonna be there.
Yeah, so it is going to be like leaderboard style, I believe. So y'all better bring your A game. It's going to be so competitive. I think I'll be there to watch
And it's
because
gonna be teams. You just gotta make sure your team's good.
sorry, not tomorrow, Thursday. I'll probably be there Thursday, I think. Yeah. So because he said that like you can put the points on any exam,
Oh, it's
his
gonna be
lectures. Hmm?
oh, it's about to be this one.
Yeah, this is the one. This is
Oh,
the
this is
one.
gonna be bad.
Well, when he told me no correction test corrections, I said, oh, they're gonna feel this one.
Yeah, yeah.
Yeah. So, but mm, I hate that I couldn't keep. I should have just put in my calendar because I'm not taking the class, but I'm like involved. I should have put in my calendar when the exam was because I know we had gotten pushed back to this week, but I could not remember for the life of me what day, what was the date? Was it the second or the fourth? And if I feel like it snuck up on us.
It's so did.
So yeah,
Yeah, it's I'm not
Harrison, you got the right idea. Yeah, it's pretty crazy. Um, so it may be helpful. I may just do a video if I'm feeling it. It may be helpful to like have a video going over hydroboration's mechanism, as crazy as it is. But if you go over it a couple times, it might help with remembering the facts better. Because this is me, just saying. When I went over the mechanism for oxymercuration, which is the other tougher reaction, once I went over it, like I remember better what's it for, how does it, what sort of product you get out of it. just now I was like, dang, what do we get for hydroboration? Because through hydroboration, the first reaction, it's only to help in uh yeah, it only helps in like setting up to get a hydrogen. The mechanism, from what I recall, off the top of my head, the mechanism is pretty complex. And the boron there kind of hangs out until H2O2 and NaOH comes in to, do the oxidation part. So it is a type of you can say type of hydration mechanism reaction.
Yeah, we're gonna see how that goes if the test asks me that tomorrow.
Well, like I said, know all the reactions.
Yeah, yeah. It's a little late now.
So I will even like this will be good to kind of note. Even if we don't go over like a lot of them, oh, excuse me. If we don't go over a lot of the other mechanisms tonight, um, again, I've done a few videos on some of these, but consider how you can uh, group them off. There's like 3, 4 different hydration reactions. They all have the same goal. They just operate differently. And then you have a couple involving a halogen, right? Ozone is very easy. So I would say like the hardest ones is hmm, let's see. Oxymercuration is not that bad once you get to know it. I would say compared to hydroboration, it's a little complex too, or let me not say complex, it's a bit cumbersome, but the mechanism is easier than that of the hydroboration reaction. So hydroboration is up there. Hydrogenation. Oh yeah, and then dihydroxylation. Yeah, we're gonna start winding down here. So I did a video. I'll double check, make sure it's added to the playlist. But I did a video on number 6. I need y'all to watch that if we don't cover it in this session. And then I could also do a video on these questions. Reactions. This is number 5 from this is both the second worksheet.
I have mine.
Awesome. So do you want to start, Sarah? You want to tell us what you got? And I can draw it out.
Sure. So what I got looks like the last one, but instead of that OH, it is just the iodide.
That's exactly it. Nice.
It felt too easy. Like, I
It's
know
because
that
it
sounds
kind of
dumb
is.
because I'm so confused, but it was like, that can't be right.
So you're following the facts, like what is happening. So do you remember what type of addition this is? Is it, I don't want to say it yet. Like, yes, is Makovnikov. It follows that type of mechanism. So if you remember that, once you identify what type of reaction it is, like, oh, it's a hydrohalogenation. You're adding hydrogen and a halogen. So halogenation. That's probably right. Whatever. I'm gonna go with it. Um, then you remember It goes Makovnikov. It's actually the very first reaction you learn in this chapter. So that should be kind of easy to remember. Okay. I'm going to go counterclockwise. Harrison, I see you have your answer. Yes. And this could be the major or the minor. What else could it be? I know there's just one box. But what else could there be from this reaction, which we'll call hydrogenation? Yes. I like how you put that. So we have a chiral center. It's going to be this one. Sorry if y'all can't really see that. So basically where the carbon with the methyl group, right? And so when we're adding the hydrogens, it is syn addition. That is one of its main like facts of it. So we're adding the two hydrogens whereby they're facing the same way. So how Harrison has it drawn the first time, he went with, they both add like, I guess you could say like on the backside. And so they are on dashes and pointing away from us. Cool. Because of the fact that we have a chiral center though, we have an enantiomer that is produced. So it would just flip, right? The methyl group would be wedge. The two hydrogens would be then, or you can say, yeah, we'll just do it like that. And then it would be dash or wedges. That's it, right? Methyl group is dash. The hydrogens are wedge, you know? So either they can touch pointing towards us or away from us. Cool, cool, cool. And that's really because we don't have a meso compound. If it was a meso compound, we wouldn't be able to showcase them as enantiomers. So that, remember, that comes from our list of characteristics: arm, a chiral, racemic, mixture, and meso. We have a chiral center. I'm going to assume it's not racemic. Could be. We definitely don't have a meso compound. If one of the three is the case, then we would not have, quote unquote, enantiomers present. Cool. So that one is done. And then we have for Seth, this hydrocorporation. I'm so sorry. I mean, but thank you for being so brave and like taking on this one. Okay. So full name, hydroboration oxidation. This is the one that I think is probably the hardest reaction to remember and deal with. The facts are this: is anti-Makovnikov. So you're already doing that, showing that here. Instead of the OH going to the more substituted side, because Makovnikov says hydrogen goes to the least substituted side, right? It's flipped. If it's anti, we're flipping it. And so now the hydrogen goes to the side with the methyl, with the more substituted carbon, and OH is on the least. And it is also syn addition, right? So unlike the reaction Sarah had, the reactions that Harrison and Seth have are both stereochemically, or well, I believe yeah. So Seth's case is it's syn addition and it's regioselective. Because of the fact that you have a chiral center, right? Chiral centers, you're going to have enantiomers as long as they're mirroring images, right? You could have diastereomers if only just the one changes. But since it's syn addition, so the other one would look like this. Okay, so let's say this is going to be totally made up, but let's say they're both R and R, and then they both flip to S and S. That would be mirror imaging. Mirror imaging, yeah. Mirroring, making them enantiomers. If only one chiral center of the two changed, they will be diastomers because they're no longer mirror imaging or mirroring each other, you know. So did you actually, Seth, actually look at the configuration?
To like help me figure it out.
Yeah, so like when you just drew the first one, you didn't have to draw the enantiomer, but with the first one, did you like confirm what the configuration of each chiral center is?
Oh no, I didn't do that.
Okay, that's fine. So we could probably, so that will be
I'll be
R.
honest, this is just now figuring out that we had to do that.
I mean, just so you can say whether you have have enantiomers or diastereomers, because
Oh,
you know what I'm
gotcha.
saying? Like they're a little different. I know that
Yeah.
like they tend to just say like, oh yeah, this example is, you just get an enantiomer, but it may not always be the case. So you have to be careful when you're looking at, examples. It's that example that can demonstrate generally what's going on, but it's not always going to look like that because every case is different. That's the hallmark of science. We have so many theories and like principles. Sometimes we forget that we really are looking at it case by case. So that's where it gets a little weird. But yeah. So the top carbon with the hydrogen in the methyl group, it's R. The OH one, you could say that is 1, 2, 3. So like that. So that looks like S. So you have RS, and then because it's syn addition, they should both flip. So yeah, so this should be an enantiomer still. Because it'll be RS and then SR. That's going to be mirroring. Remember, enantiomer,
Yeah.
both of them have to change. Yeah.
Gotcha.
So,
Okay.
yeah. So you still have an enantiomer there.
Cool.
Yeah.
Makes
Yeah.
sense.
Cool, cool, cool. Yeah. So hydroboration has like so much going on. Um, right. It's
Yeah.
anti-Makovnikov's in addition, regioselective. Harrison's case, I think, is more stereo selective. It would be considered stereoselective. Look at what that means. I swear this keeps wanting to fly off. All right. Yep. So with Harrison, your reaction for hydrogenation, it's syn addition and it's stereo specific. So yours has more to do with what is the stereochemistry given, you know, what what we have versus regioselectivity. That is something of concern in the early stages of the mechanism and the, getting the product. Okay. And I guess you can argue in terms of the with determining the major and minor product for Seth's reaction on hydroboration. Yes, it's regioselective, but it could also be stereochemically selective, right? To see like what is the major product. Although I don't think you had to answer that. Nope. You did not have to answer what is the major product. You only had to worry about producing the desired compound. So y'all did that. So great job. Y'all actually got that, you know. Um, okay. So what questions do y'all have? What thoughts do y'all have as well?
Feeling a little bit better. Tired.
Same. I'm glad you're feeling better though, Alkenes.
Yeah. Yeah.
Oh, it's
I'll be
good.
okay.
You will be okay. Promise you will be okay. So I know now he's curving exam 3 as well. That's so generous.
I hope it's
Like,
heavily.
look, man, like this has been amazing. Like, just the way that y'all have had it here and at a university, it has been the most cathartic thing because, like, the experience of it can be so tumultuous. I swear y'all had it better. Y'all had it better.
I definitely enjoyed this organic chemistry class a lot better than even my Gen Chem classes in Hattiesburg.
Wow. That's pretty amazing.
Just like it made it easier to learn.
I think that, you know, so when they make it tough, this is just what I've observed and now even research. They make it tough by, I don't know, you can say like not really sometimes teaching it to a good depth. Obviously, you're going to have to cover a lot of material in a short amount of time. That unfortunately is going to be the case every time.
Hmm.
Not saying it's like totally out of our control, but it's kind of out of control. Um, but yeah, like the issue is how it's taught. And I mean, no fault to some of the teachers a lot of times, but some folks are not really given proper training on pedagogy, especially for higher education. So if if people aren't provided like good professional development or mentorship or opportunity to observe, they're missing out on skills that can actually help make this meaningful. And so the rigor part really comes from being able to comprehend this and like work with the material. It's not about the like material, the material of it is daunting because it's a lot. But like actually knowing the material, in my opinion, is not that bad once you like get to know it. It's just how it's taught. That's just it's
For
kind of
sure.
how it boils down to. Yeah. But then also I have to play, whatever they call it, devil's advocate. I've been there too. I'm still that, I'm still a student. Like y'all have to have the right skills too.
For sure. For
You know what I'm
sure.
saying?
Yeah.
So it's not just on the teacher and it's not just how it's taught, it's how the student is working with the material.
Yeah.
So, you know, and I know part of that is time management and just taking care of yourself. But then, of course, the other thing is how do you study? How do you study for STEM? You know, that's
Consistency. Gotta be
yeah,
consistent. Yeah.
yeah, yeah. That's definitely a big one. It's definitely a big one. Um, so that's what we're constantly trying to study and figure out. But that's something that y'all need to be taught as well. I don't think that's just something you just come in and like, you know,
Oh, for sure. Yeah.
yeah.
Sure.
Yeah. So it's a lot of things, but it's not that bad, y'all. It's really not that bad.
We'll be all
Oh,
right.
I say this like years later. Yeah. No, y'all are good. Y'all are good. So y'all did great here. I think this is like the little annotation thing. Yeah. Okay. So I am going to clear this. So what were some other, as we kind of wind down here, but what were some other like questions or thoughts that y'all had about the exam?
Mm,
And while you're thinking stuff, Harrison, did you, I know we didn't like really get into it, but from some of the example practices we did, do you feel a little bit better about nucleophiles? And there was the other table too, but understanding like nucleophile base, even though we focused on substitution mechanism. Sorry, let me check the chat. Cool. 75% is good. That is good. So, ooh, how did I miss this? This is cool. Okay. So you have this table, and let me show you on the playlist. Oh, what does it say? Oh, I hope I added it. I hear my voice screaming at me through this video, so I had to pause it. Okay, maybe okay. Yeah, this is the one. So it's in that playlist. Again, Sarah, I'll make sure to send it to you. It's in this playlist selected exercise. So this one I actually cover kind of in depth how to answer 6. This is from the worksheet 2. And this is a good one to actually cover for the exam. Hint, 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 hint. This is one that you've seen from lab, right? For one. And this is kind of interesting because I know that this earlier, I remember. This one is a tertiary substrate, but it's undergoing technically an SN2 reaction. So it doesn't tell you what reaction. You have to discover that for yourself. I think this table is what kind of helps determine like, okay, if you have this type of nucleophile base, what sort of reaction do you get? Now it says, hold on, let me see here real quick. Yeah. So it says that tertiary would not undergo SN2. However, that is like very generalized because the question, I mean, let's see. SN2, let me say strong nucleophile. I may have to revisit them. This is interesting. Okay. So there was master. I think this was the one. All right. So this is going over, given it undergoing SN2, what sort of rate would you see it undergo? And that is what this video is kind of getting at as well. And it's interesting because I want to revisit it again, actually. Yeah, I may get an email about this if I do come up with something. But yeah, so obviously for tertiary, when it comes to the SN2 reaction, you're not going to see anything immediately, right? It's the steric hindrance that is the reason. However, that doesn't mean it just won't happen. So this table is quite interesting considering that. Once you determine which mechanisms be favored by the reagent, analyze the substrate. It's funny because I would start with the substrate and then look at the reagent. But they say you start with the reagent and then analyze the substrate to see what would dominate. So based on this data, or let me not say data, based on this general table, it's saying it will not undergo SN2. It's saying it could undergo E2. Now that's saying elimination. But here we have, okay, what if it is subject to an SN2 mechanism? The relative rate is less than 0.001. So it's going to happen so late, the reaction to actually substitute, right? So that is a possibility as well. And that's why, in my opinion, I think this problem is so tough. Okay. So feel free to watch it. And I reference Master Organic Chemistry. I referenced this source in the video. That was probably the one other thing I wanted to say. But I know that we are at our wits' end in this what you call it, in this this tutor session. Okay. So yeah, definitely make sure y'all have this table down. You practice a little bit. I think we're good. There's nothing else.
Thank you so much, Gabby.
No problem. Thank y'all for your patience and effort and just, yeah,
Thank
giving yourselves a chance. Yeah.
you.
Yeah.
I got
I think,
grade.
yeah, you're good. You're good. I think the slides are helpful, but yeah, if you just kind of like hit up some of the practice, you'll feel a little bit better about actually approaching it. It's like trying to do the test itself almost. So I think you'll be okay.
Okay.
Yeah.
Thank you,
All
Gabby. Have
right.
a good night.
You too. You too. I'll see y'all tomorrow.
Thanks.
No problem. Take care, y'all. No problem. Good night.